Introduction: technique to create prototypes that have not yet been perfected. However, there has been a form and new vectors with the frame. The system's spatiality generated from the tensile forces acting on the fabric within the frame. Our objective is to develop a machine capable of generating components through patterns interacting via a system of local rules that define a heterogeneous and differentiated space. The prototype, one-to-one, will be supported by a computer program simulation. Background: Forceflow CAST is working with catenary systems, which we have extensive background to support our research and work. Earliest use of catenaries date back to Sir Christopher Wren, an English architect who designed the dome of St. Paul's Cathedral during 1675. Here, the system of piers had been shaped in part according to an inverted catenary. During the 20th century, Anthony Gaudí, between 1889 and 1908, designed the colonial well church with a highly innovative method, the hanging model, which is based on the theory of the reversion of the catenary. A chain suspended from 2 points will hang spontaneously in the shape of a so-called catenary. Only tension forces can exist in the chain. The form of the catenary upside down gives the perfect shape of an arc of stone masonry, and in such an arch, only reversed forces of tension, being compression, will occur. In Gaudí's hanging model, a system of threads represents columns, arches, walls, and vaults. Later, during the 1940s, Spanish architect Félix Candela developed and perfected hyperbolic ceilings. His greatest contribution to the structural field have been the shell-like structures, generated from the hyperbolic paraboloid. A geometric of extraordinary efficiency have become the hallmark of its architecture. Between 1950s until late 1970s, German architect and structural engineer Frei Otto made experimentations with light-weighted structures for ceilings made of chains. Their own weight will dictate the form of the structure. These models were computer elaborated by programming software and compared with one-to-one models. This was able to distribute loads. It is also reverse of the catenary system. Meanwhile, Hayes Eisler, best known for his amazing freeform shell structures, worked from definition of mere structural engineering to the extent of becoming structural art. Rejecting the use of mathematical formula, he approaches the challenge of new structure by using physical modeling to determine the form and subsequently to investigate its stability. Recently, in 2009, the Architectural Association's Design Research Laboratory in London made the latest attempt and experimentation with catenary forms. They worked with fabric tensile structures generated by computer pattern. They printed, sewed, and filled with liquid plaster. The process and materials used are the same ones we are applying. The prototypes, including frames, lycra, patterns, dots, and stitches that control the pouring plaster to create the desired form. Research structure. Procedure. In order to create catenaries, the first step consists of assembling the wooden frame. The second step consists of cutting the canvas and making a grid. Then draw linear and non-linear patterns after sewing the blanket. The next step is to place the fabric in the frames controlled by tension. Variables consist of forms and spaces. Thickness controlled by dots and stitches. Materials cast of heterogeneous mixtures, patterns and local rules. Flows and forces controlled by tension and openings. After placing the canvas, we have to fill up with an heterogeneous mixture of plaster and water. We made experiments with other materials like cement, fibers, concrete, plastic, and polyurethane. And we used aggregates like elastic rubber, styrofoam, rubber, and sawdust. Finally, after the plaster dries, we remove the fabric. Stages. Stage 1. Process replication. Replicate experiments performed at the Architectural Association in London to understand linear patterns. These patterns had no logical sense but helped us define what needed to be done. Stage 2. Pattern exploration. Prototypes done to understand our own patterns and how would the cast flow work according to dots and stitches. These weren't really patterns as they were mostly intuitive and random. Stage 3. Pattern evolution. Nature-inspired patterns were our next test, but the ones we used, like patterns on how trees grow, were still too linear. We also tried to make different forms to achieve new ways to connect several pieces. We noticed that we had to think of more flexible and adaptable forms and materials. Stage 4. Material development. We started to think of materials and aggregates to make the mixture more heterogeneous and lighter. From these tests, we discovered that the plaster with cement worked perfectly fine to make the mixture lighter. To develop connections, we placed wire and in some cases metal mesh in the unions between two pieces and then made the cast with a mixture of plaster and cement. At this point, our fabrics resembled leg components due to the way we tensed the fabrics. Experimentation. We made a couple of experiments to take the system 1% ahead of what's done before. Experiment 1. Aggregates. As we were looking for a more flexible mixture, we had to think of different aggregates. However, we also had to think of something that wouldn't make the mixture more brittle. Plaster itself is not very resistant, but we found that small styrofoam pieces, around 2 mm in diameter, could give our mixture a different texture, while rubber or sawdust would only break pieces apart. We continued working on patterns and openings in the fabric. This way, patterns began to make more sense while openings had barely sense. Next step was to scale up, move on to the next level. Experiment 2. We attempted to join the two systems together, but each system had its own unique behavior, pattern, and local rules. The problem with the union between these two pieces was that the concentration of mixture in the union made the component heavier. Another option was to make a monolithic piece. Though the result was successful, we got a monolithic piece of larger dimensions, twice of the previous efforts, hanging on a larger frame. The problem with this approach was the amount of material needed. Conclusions. Of the materials used, plaster with cement with an aggregate, in this case styrofoam, works better and gives a spongy consistency. In the case of patterns, the closer the stitches and dots are, the less is the thickness of the structure cast. A degree of control over form is achieved by the tensions and patterns applied to the blanket. What's next? Local rules. For example, how does a dot work next to a stitch? Or why the distance between two dots? Nonlinear patterns or flows. Transparency given by paraffin. How will these components stand still without the frames? Connections between elements. Computer programming of the machine.